This fourth lesson on power series is just a little micro lesson. I think that sometimes when you're working with power series, it's easy to get distracted by the sigma, that big Greek E, if you will. And it gets overwhelming, the notation gets scary, and I think that it's easy to lose track of what you're doing with the power series. The key is that a power series does not require a sigma. A power series is just an infinitely long polynomial. Um, all the sigma does is the sigma provides you a nice way of taking something that's infinitely long and writing it in a nice, concise, clean manner. So the sigma is a notational mechanism to help you, though sometimes it doesn't feel like help. So in this particular lesson, we're just going to focus on those coefficients and see how if you focus on the coefficients, you can find a power series, even if maybe sigma never shows up in the lesson. All right, last question from this section. Example 6. I want to solve f of x equals f prime of x using power series. This is technically not a traditional calculus question. This is actually a question you'll see kind of in differential equations. But I think it's a nice example because of the fact that it's going to invite us to think about those power series in a term-by-term manner, which is something we talked about earlier, but haven't really touched in quite some time. So this term-by-term approach is going to be a precursor to what we're going to do later on. So let's think about it. If we're working with power series, then that means that f of x must be equal to some c naught plus c1x plus c2 x squared plus c3 x cubed plus dot, 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 dot. Okay, and we don't know what the c naught, c1, c2, c3 are. Those are the constants that we need. But if f is indeed this kind of power series, then that would imply that f prime of x would equal, well, we just have to take a derivative. So we would have the derivative of c naught is 0. So then derivative of c1x would be c1 plus, it looks like 2c2x plus the derivative of c3x cubed would be 3c3 x cubed. We start to, or x squared, pardon me. Start to see the pattern emerging. Plus 4c4 x cubed plus dot 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 dot. And then what we're going to do is we're going to set up a series of like an infinite number of equations. So notice what's happening here. If we match the x terms and the x squared terms and the x cubed terms, okay, even the constant terms here, what that's going to tell us is that we can match the coefficients. So you can see that c naught must be equal to c1. C naught equals c1. And then if you look at the next terms, c1 must be equal to 2c2. c1 must be equal to 2c2. c2 must be equal to 3c3. Okay. c3 must be equal to 4c4. Et cetera, et cetera, et cetera. So what does et cetera, et cetera, et cetera mean? Well, it looks like it means that Cn will be equal to n plus 1 Cn plus 1. Okay, let's see if we can understand where to go from here. Let's see if we can put everything in terms of C naught. So if we want to put everything in terms of C naught, notice we're going to start with C naught, and then we know that C1 also is the same as C naught. And how about C2?
Well, C2 is equal, C1 is equal to 2C2. So we could divide by 2, and so we'd get 1 over 2 C1, or in other words, 1 over 2 C naught for our C2. How about C3? So C3 here, I'm looking at this equation. So I'm going to solve for C3. So C3 will be 1/3 C2. And we've already found that C2 is 1/2 C naught. So this would be the same as 1/3 times 1/2 C naught. Okay. How about C4? So here I'm looking at this relationship. And so C4 would be 1 over 4 C3, and 1 over C3 would be the same as 1/4 times 1/3 times 1/2 C naught. I'm hoping you're seeing the pattern here. So it looks like if we went all the way down, it looks like if we went to Cn, we would get 1 over, well, if I had 2, I had 2, which is the same as 2 times 1. If I had 3, I had 3 times 2, 3 times 2, 3 times 2 times 1. If I had 4, I had 4 times 3 times 2 times 1. So you're starting to see factorials. And so Cn would be n times n minus 1 times ... times 3 times 2 times 1 C naught, which would be the same thing as 1 over n factorial C naught. So let's see, and notice every single one of these terms has a C naught in it. So there's like a constant factor. So that tells us that our f of x is going to equal some coefficient C naught, which we don't know, and then we're going to be left with 1 plus C1 is, 1 C naught, so I've got 1x or x plus C2. C2 is 1/2, which is the same as 1/2 factorial, x squared, plus C3, which is 1 over 3 times 2, or 3 times 2 times 1, which is 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the 4th, plus ... on and on forever and ever. Or in other words, we've got that this thing is equal to C naught, some constant, times the sum from n equals 0 to infinity of 1 over n factorial times x to the n. And so you have solved this equation up above, this what's called a differential equation, where it is f of x equal f prime of x, and you have a solution without knowing anything else about the equation. Interestingly enough, our f of x, we will play with this. I think you already played with it back in the previous quarter, but you'll play with it in differential equations. And we'll play with it with Maclaurin series as well. Our f of x here is actually c times e to the x. That's what this, or I guess it'd be c naught times e to the x. That's what this function is that we're messing around with. But we don't need to know that it's c naught e to the x in order to find the power series expression, a solution that we found. So note, in this solution, we took a term-by-term approach to finding the coefficients C naught, C1, C2, C3, Cn, etc. That is, we found kind of an expression for each one of those coefficients. This has the same end result as finding a nice clean formula, sum from n equals 0 to infinity of Cn x to the n. It's just that the notation where we find all the C's is not quite as concise as the notation where we have the sigmas involved. So, historical note. You may recognize the question above as a differential equation. Power series provides an extremely powerful technique for solving differential equations that can work on many, many questions. It frequently isn't the fastest or cleanest approach, but it works. This is why power series have historically been that Swiss Army knife or duct tape of functions. They work in a wide variety of situations.
So again, this is a really short lesson. The purpose of it was to remind you that that power series are about finding the coefficients to an infinitely long polynomial. If you happen to be able to write it in sigma notation, great. But if not, that's okay too. The specific example we were working with comes out of differential equations, and just as a little bit of a foreshadow, remember that was f equals f prime. Where have we seen this before? Well, in differential equations, maybe you've seen it, but even without that, like what function is equal to its derivative? Let's think about it. There's a very famous function or family of functions that are equal to their derivative. And so we just found a power series representation for a new function, which is pretty rad.